So I took this little snippet of text here from the Wikipedia page on ellipses. So, and they say more generally for an arbitrary oriented ellipse centered at V, it is defined by the solutions x minus V transpose A x minus V equal to 1. So, V is the center of the ellipse, and then the first eigenvalue of the matrix A is the length of the major axis, and the second eigenvalue is the length of the minor axis. and if we say the points that satisfy less than or equal to 1, those are all the points on the interior of the ellipse. And I think at this point in the class you would notice this equation is the same equation as the Mahalanobis distance between x and v, where A is a weight matrix, and also it would look a lot like the F statistic. So take, for example, if I were to take the hypothesis H naught K beta equal to M versus HA K beta not equal to M, which we've discussed previously. Remember, our variance of K beta hat is equal to K x transpose x inverse K transpose times sigma squared. And then what we saw was that, so then K beta hat minus M transpose times K x transpose x inverse x transpose, not x transpose, K transpose times sigma squared times K beta hat minus M. Well, that follows, inverse here, that follows a chi-squared distribution with the number of rows of K degrees of freedom, and then if we divide that by its degrees of freedom, which is, let's just say the rank of K is, let's say, V. So divide by its degrees of freedom, then divide it similarly by n minus p s squared over sigma squared, which is also a chi-squared, and then divide it by its degrees of freedom, which is n minus p. Then we have the ratio of two chi-squareds. This part is a chi-squared with v degrees of freedom. This part is an independent chi-squared with n minus p degrees of freedom. And then let's organize terms. And again, we've already done this, but it's good for review, I think. If we organize terms, what we see is that that sigma squared cancels with that sigma squared, that n minus p cancels with that n minus p, and then we get that k beta hat minus m transpose k x transpose x inverse k transpose inverse k beta hat minus m over divided by v s squared. It follows an F distribution. With v numerator degrees of freedom and n minus p denominator degrees of freedom. So we would reject this hypothesis k beta equal to m if this is greater than or equal to an F critical value of 1 minus alpha n numerator v numerator degrees of freedom and n minus p denominator degrees of freedom. And so we would accept the null hypothesis. We'd accept this hypothesis if it was, let's say, if it was less than or equal to. Sorry, it probably should have been greater than for the other direction. Okay, so I could divide this by f1 minus alpha. You know, it's already divided by vs squared, and divide it by f1 minus alpha v n minus p, and then we get less than or equal to 1. Okay, now we're just back up to this equation again, and so what we see is that the set of values of M for which we fail to reject the null hypothesis forms an ellipsoid. They form the interior of an ellipsoid. Okay? And so that is given a term, it's called a confidence ellipsoid. Okay? And so a confidence ellipsoid is just a confidence interval, the generalization of a confidence interval to more than one dimension. Okay? And we see that the form is pretty easy. Here it's, our k beta hat is observed. Our m is the variable that's varying. Okay? And then this entire matrix right here is the A matrix from before, from the Wikipedia definition. So if you had, say, software that would, for a given, take in k beta hat and A and plot a hyperellipse, say in 2 or 3 dimensions, then you could create hyperellipses for those settings. And we'll show in a coding example next how to do that in 3 dimensions, just because it's kind of neat. But there's a couple of times that you might want to do this. A good example is when in, say, linear regression, where you want a joint confidence interval for the intercept and the slope. But also notice if you have 2 x naught values, let's say x naught 1 and x naught 2 transpose, right? If I take those times beta hat, then I get, say, y naught 1 and y naught 2. So if I want to predict my confidence surface at 2 points, okay, then I might want to do that, a joint confidence surface for that, okay, and then just to get a confidence ellipsoid. And this is just a special case of this formula. And of course, if you wanted to generalize a confidence, a prediction ellipsoid, I think you could all do this at this point, given this knowledge. So in the next lecture, why don't we go through and create a confidence ellipsoid in this specific case. And I think it'll be pretty neat because we can use RGL and show how the confidence ellipsoid looks in 3 dimensions.